I keep on losing signal here. Let's see. I'm using my hotspot right now. It looks like the hotspot has a stronger signal. Let us hope it doesn't fall off, right? And let me know. Let me know if you continue having any problems with my transmission here. What we are going to do now, let's do an example. There you go. And the example involves a satellite. Here you go. We have two satellites at 2 degrees apart from each other. Find the arc length between them. And by the way, those satellites are in geostationary orbit around 42,300 kilometers from the center of the Earth. Okay, so let's see. I can. I'm gonna illustrate the case so you can understand, have a better understanding of what the problem looks like. Okay. So no, that's not what I want. That's the drawing. No. Home. No. Pictures. Drawing. Okay, good. So here you go. Drawing. This one right in here. Okay, so here you go. Here's this Earth. Okay, we have one satellite here, another satellite here. They're both at the same distance, and their angle is 2 degrees. That's the insert shapes. Drawing. Here you go. Like that. Okay, and yeah. Okay, and then we have this other satellite. Like that. Right, yeah, here you go. 2 degrees. Okay, so going back to the enunciate of the problem. Right? Find the arc lengths. He's asking the arc lengths between them. He's not asking the linear distance from each other, right? The arc length is one thing, the linear distance is something else. It's going to be something else. And yeah, okay. Now here you go. The arc length, I'm going to put here this guy on the center of the Earth, right? So I can have a realistic drawing. That's going to be difficult. Let's see. View, I want to get that grid line. Yeah, here you go. I'm going to put the planet Earth at the center of the, yeah, here you go. This one here. Yeah. Okay, better. Now I'm getting there. Here you go. That should be the arc length right in here. That's the arc length. It's not the straight line between the two satellites, but the arc length that you see right in here. Okay, so just go back to our, this is a straightforward problem. You just use one equation, no more than that. And the angular displacement between those satellites is 2 degrees. And let's go get the equation. Here you go, right in here. This one right in here. Solution, 42,300 kilometers, 2 degrees apart, but let's not forget that an angle should not be written down in terms of degrees. Instead, it should be written down in terms of radians. Here's 42,300 kilometers. I'm going to write down 2 degrees here, but this degree must be converted in radians. And in order to convert this degree in radians, what do? We have to multiply by 2 pi and divide by 360 degrees. That's how we convert one into the other. Okay. This degree cancels out this degree here. This degree here can be treated as a unit, okay? This degree cancels out this degree, and we end up having the arc length in kilometers. Okay, so step by step, you go 2 degrees cancel out with 360 degrees. What was 360 degrees become the number 180. Two here cancel with 180, becomes 90. 90, pi over 90. This 0 cancels out with this 0 here. With this 0. And, let's do an approximation, right? Pi is approximately 3 divided by 90. is approximately 1 over 30. 1 over 30, 4,230 divided by 30. That's kind of a straightforward problem. So let me do that exactly how in my calculator. 4,230 divided by 90 times pi. Okay, I'm getting 147 kilometers only. It's a very small angle. So I'm not surprised that we are getting this small number, 147.7 kilometers. Okay, let's see what we have in my notes there in the back. Here you go. Yeah, 1,476 that I'm getting, that we got. And here you go. Hey, wait a minute. Let's see here. I got 1,000. Why did I get 1,000 here? Let's see. Oh yeah, it looks like I made a mistake here in this one. Let's see here. 362 pi radian, 2 degrees is x. Yeah. X is going to be 2. Okay. I don't see any mistake. It's just the formulas are correct. The problem here is just the numeric value. Okay. So let's see. 2 degrees. 2 degrees. Right. If we go back, let's go back here to this one. I like the way I put it here. No? 360 degrees. 360 degrees to pi radian. 2 degrees is x, right? So for x, and x is going to be 2 pi radians, is this one right in here, divided by 360 degrees, multiplied by 2. Okay, no problem. So why am I getting the different numeric result? Let's see why we're getting the different numeric result. 2 cancel with 2. 2 degrees cancel is 360 is 180. That's all right. And then we are left with 2 pi over 180, pi over 90. Ah, okay. So I made a mistake here. Okay, yeah, okay. So there's a mistake right in here. Okay. 2 cancel with 108, so you get pi over 90. And now, okay, the 0 of the 90 cancels out with the 0 of this guy here. Right? That. And now 4,230 times pi divided by 9. Okay, now I got it, what I got before. 1,476.54 kilometers. That's the arc length between the two satellites. And let's move to the next one. Here are the sections of chapter 8 that we covered so far. Okay, and rotational motion and angular displacement, we covered that. Okay, good. Angular velocity and angular acceleration, we covered that. The equations of rotational kinematics, uniform rotational motion and uniformly accelerated rotational motion. Angular variables and tangential variables, we did that too. Centripetal acceleration and tangential acceleration. Okay, so let's skip rolling motion, okay, and we're going to skip this one as well. Yeah, let's stick with those 5 sections here. So we covered everything of chapter 8. We're done with chapter 8. And now chapter 9. Let's start with chapter 9 now. Rotational dynamics. We did rotational kinematics, and now we're going to do rotational dynamics. And let's take a look at the sections of this chapter. Let's see here. Yeah, okay. Those are the sections of this chapter. Action of forces and torques on rigid bodies. Okay, the idea of torque here is what I like to call the angular force. Okay, so let's review what we have talked so far. We talked about 1, angular position. 2, angular displacement. 3, average angular velocity. Instantaneous angular velocity. Average linear acceleration. Instantaneous angular acceleration, right? What else we talked about? We talked about uniform, not uniform motion, but uniform angular motion, right? Uniformly accelerated motion, not uniformly accelerated motion, but uniformly angular, uniformly accelerated motion. Angular, uniformly accelerated motion, right? Equations of motion. We talked about the equations of motion as well. Conversion of linear quantities into angular quantities, and vice versa. Vice versa. So what we're going to start doing now? Well, we will continue with this we'll continue with this conversion from linear to angular, right? And the first one that we're going to talk about is the force, the angular force. The angular force has a name, and we call it torque. Remember that. Torque is the angular counterpart of the linear force. Torque is the angular counterpart of the linear force that we saw before. And we have to look at its definition. The best way to understand torque is by thinking in terms of real-life applications of torque, okay? Yeah. And here you go. There is an illustration right in here. Okay, let's see. I want to show you this one here. Here you go. Suppose that you have a door. A door is a rigid body. Okay, and this door has an axis of rotation that's placed exactly where the hinges are located. The hinges of the door are located. Let me take it out. Consequently, the axis of rotation passes through right in here, the hinges. Here you go. Here's the axis of rotation. Okay, and the door can rotate about that axis. Can be in one direction or can be in the other direction. It doesn't matter. Looking from the top, the door looks just like that, right? The door is very thin, and it can rotate about this axis right in here, okay? Either in the counterclockwise direction, or if you look from the bottom, here's your if you're looking from the top. Oh, wait a minute. If you're looking, in both cases, you're looking from the top. If the door rotates in the counterclockwise direction, okay, you apply your right-hand rule, and you, if the door is using your right-hand rule, it is as though as you're seeing your thumb pointing towards it. Okay, so here, this point that you see here is the direction of rotation and indicates your thumb. Now, if the door is rotating on the other direction, in the clockwise direction, we say that the arrow of rotation is into the board. Okay, so here's the tip of your arrow, and here is the back of your arrow, right? Just like the eyelets of an arrow. That's the type of notation that we use to discern between counterclockwise direction and clockwise direction. The counterclockwise direction is said to be the positive direction, and the clockwise direction, the direction that the hands of the clock moves, is considered the negative direction. Okay, let's write that down. For torque is the angular counterpart of the linear force, okay? A torque can either be in the positive direction, counterclockwise direction contrary to the motion of the hands of the clock, okay? Or can be in the positive direction or in the negative direction, clockwise direction, okay? The positive and negative directions can also be visualized by the right-hand rule, okay? Come on. One, positive direction is that the one, the thumb of your right hand points towards you, right? So here you go. Here my thumb, right? I'm gonna look into my thumb. I'm gonna apply my right hand rule. I curl my right hand in this direction, and the thumb is pointing towards me. So, the hand is moving the counterclockwise direction. Consequently, it is the positive direction. Okay. Now, if now you if you look in this direction right in here, right, you're still moving according to the right hand rule. Here you go, still moving according to the right, and I'm looking at the back of my hand. It is as though the palm of my hand is moving the clockwise direction. And now I'm not looking directly at the thumb because my hand is in front of my thumb, right? Two different ways of visualizing this positive and negative direction, either in the clockwise and counterclockwise direction or by applying the right hand rule. Okay, positive direction is that the thumb of your right hand points towards you. Okay, negative direction is that the thumb of your right hand points away from you. That's what you have to know. So here you go. And what else do we have to know about the torque? Okay, the torque is a type of force that depends on the position of the application of the force. Okay, suppose that you have here this rigid body. Here you go. And I decide to apply a force at this point here at the door. The door will tend to move in the counterclockwise direction, right? And what does this mean? It means that when we apply a force here, I'm also applying a torque to this door. Okay? And depending on the position that you apply this force to this door, you're going to have more or less torque. Have you ever experimented that with the door? It's much easier for you to open a heavy door if you apply a force here at the very tip of the door, right? Why is that? Because it makes your torque larger. The larger the distance from the axis of rotation, the larger the torque becomes. The closer the point of application of a force is to the axis of the rotation, the lower the torque becomes. It's far harder to rotate a door if the point of application of the force is closer to the axis of rotation. Okay, that's the qualitative view of the torque. And now we can start talking about the mathematical. Here you go, the mathematical definition of the torque. The mathematical definition of the torque depends on the distance from the axis of rotation and the magnitude of your force. Okay? That's what you have to know. But it also depends on the angle that you're applying the force. Here you have one torque. Here you have another torque. Here you have another torque. The highest torque you get whenever this angle between the force and the vector position of the point of application of the force is 90 degrees. That's the highest torque that you get. Okay, here you go. That's the angle, theta. So the torque is defined in terms of this angle theta between the vector position and the vector position of the point of application of the force and the force itself. Remember, it's vector position of the point of application of the force, right? If the force is being applied right in here at this spot, the vector position of the point of application of the force is that vector that goes from the axis of rotation to the tail of the force vector. And the angle is determined by putting both vectors tail to tail. Okay? So here you go. Now, there is another, let's do another example. Here you go. Instead of having a 90 degrees angle, let's make it this angle right in here, right? So here you go. Now, the angle between the force vector and the point of application of the force is this one here that you see right here. Okay. And what's going to be the equation? Let me redo it. Here you go. What's going to be the equation? I'm going to write that down for you here. The equation for the torque is the following. I'm going to copy it here. That's is going to be RF sine of theta. Okay? 2000. Equation for the torque. For the torque. Equation for the torque. The torque is usually represented by the Greek letter tau, and it's given by the the magnitude of the vector position of the point of application of the force with respect to the axis of rotation times the force times the sine between those two angles. Like that. Okay? So from the equation above, comma, if you increase the force and keep everything else the same, comma, you increase the torque. Okay? If one, you increase the force and keep everything else the same, you increase the torque. Two, if you increase the point of application of the force, right? Point of the application of the force with respect to the axis of rotation, okay? With respect to the axis of rotation, comma, you increase the torque as well. Okay? From the equation above, R is the distance of the point of application of the force to the axis of rotation. And theta is the angle between the force and position vectors. Force F, and position of application. Position vector, position of application of the force, position of the point of application of the force, of the point of application of the force vector, of the force vector. Accordingly, comma, if you increase the force and keep everything else the same, you increase the torque. What else? For R and F constant, torque is maximum for theta equal to 90 degrees. Okay? I presume the transmission is better now, right? Hopefully the transmission is better now. Now I'm using the hotspot of my cell phone. Looks like the Wi-Fi of the hotel is terrible here. Okay, so let me know if keep on fading there, my voice fades or not. Okay, I'm gonna need this thing for tomorrow. Very, very important that I know that my internet is working well, because I'm gonna have a very important meeting tomorrow. Okay, so now there's something interesting about the torque. We have three important cases, okay, for a rigid body. Rigid body have different behaviors when it comes to equilibrium, okay? Here you go. An object, here you go. An object is a point object. Let's put it this way. A point object is in equilibrium. We saw that before. Whenever we say that a point object is in equilibrium, whenever the net force applied to this object is zero. Okay? That contrast, this contrast with the equilibrium of a rigid body. Okay? For a rigid body, it's not enough that you have a net force equal to zero. For a rigid body in equilibrium, for a rigid body in equilibrium, comma, it's not enough. It is not enough that the net force applied to it is zero. You need more than that. The net torque needs to be zero as well, okay? And I'm gonna give you some interesting, I'm gonna show some interesting examples, okay? So for a rigid body to be in equilibrium, for let's see here. Let's put a table so you can understand better, right? Tables are very good to help you grasp an important information. Let's see how I'm going to do that. Insert table, equilibrium, non-equilibrium, point particle, rigid body, like that. Equilibrium, non-equilibrium, equilibrium. Before we started the rigid body, we were assuming that our objects were point particles. Okay, keep that in mind. Point particles, point particle, rigid body. Rigid body. Condition for equilibrium. Condition of equilibrium for a point particle, the net force, and I mean the vectorial net force, right, must be equal to zero. Okay. For a point particle, to be in non-equilibrium, the net force must be different of zero. For a rigid body, you have to have two conditions. The net force must be equal to zero, and what else? The net torque is also has to be equal to zero. the sum of all torques. Okay, and torque is also a vector. Okay, equilibrium, non-equilibrium. You know, for a rigid body to be in non-equilibrium, you can have two situations, right? Either the force must be equal, different of the three situations, and the net torque equal to 0. You can have net force different of 0 and net torque different of 0, right? And then we have this other situation here in which net force is equal to 0 and net torque is different of 0. In this case, the rigid body would either be rotating with constant angular velocity. Okay, here you go, constant velocity, right? Constant velocity for the point particle here is going to be point particle either at rest or moving with constant velocity, right? Here too is the same thing. The rigid body would be either at rest, not rotating, or moving with constant angular velocity. Okay, that's and I can illustrate one case for you. Let's see if I have it here. Let's see here. Let's see if I have it. Oh yeah, I have it here. That's what we call translational equilibrium and rotational equilibrium, okay? There's a way, here you go. In this case, here you go, look at this. Consider like this rigid body, right? And this rigid body is free to move about this axis right in here. This force is applying a torque that's clockwise. This other force is applying a torque that's counterclockwise. Okay? And their torques are the same. It's just that one is contrary to the other. Consequently, this object is in rotational equilibrium, but it's not in translational equilibrium because this whole set can move. Can be accelerated from the left to the right. Okay? Keep that situation in mind. You should be able to interpret what we see here. Next, we have this case here. In this case, the object is in translational equilibrium. Why is it in translational equilibrium? Because the net force applied to this object is 0. This force is from the left to the right, this force from the right to the left. Both forces have the same magnitude. So the object is not accelerating linearly. Okay. However, it is going to rotate. It is going to rotate because this force is impinging a clockwise rotation to this object, a clockwise torque, and this other force will enforce this clockwise torque. Consequently, this object will become uniformly accelerated, angularly accelerated. Okay, so it is in translational equilibrium, but not in rotational equilibrium. It's not in rotational equilibrium because it has an angular acceleration. What about this one? Let's take a look at this one. In this case, the object is both in translational equilibrium because this force is countering this other one here, but it's also in rotational equilibrium because this force is applying a torque that clockwise, and this other force is applying the same torque that counterclockwise. Do you see the difference here? Okay, keep that in mind. Okay? Keep that in mind. An object may have a net force equal to 0, but it may not be in rotational equilibrium. Okay? So going back to our notes here. One the other. Note C, right? Note C that an object may, one, be in translational equilibrium, but not in rotational equilibrium. Be in rotational equilibrium, but not in translational equilibrium. Okay, translational equilibrium. Equilibrium, here we go. This one, but not in rotational equilibrium. Recall, the examples in the PowerPoint images. Right? Okay, so that's and an object will be, and an object, and 3. An object will be in rotational and translational equilibrium only when the net force and torque applied to the rigid body is 0. Equilibrium. Like that. They call the examples in the PowerPoint images. Okay, we can. Okay. Here you go. If the net torque is equal to 0, but the net force is different of 0, there is no net equilibrium. In this case, the rigid body does not rotate, but it accelerates. Right? That was net force equal to 0, but net torque different of 0. Also, there is no net equilibrium either. In this case, the center of mass of the rigid body is either at rest or moving with constant velocity, but the rigid body has an angular acceleration. Non-rotational equilibrium. Hey, let's put here non-rotational equilibrium. Net force and net torque are equal to 0. Its forces must be applied at specific places on the rigid body, which has a center of mass that's either at rest or moving with constant velocity. On the top of that, neither does rotate or it does not rotate. Either it does not rotate or rotates with constant angular velocity. Okay, keep that in mind. And now we are ready to start to apply Newton's second law of motion to rigid bodies. And that's what's going to come next. Here you go. Let's take a look, but before we do that, let's take a look here at this other example in the book, okay? It's a nice example. Here you go. Here's the object. It's a board, rigid body. I'm going to copy and paste right in here. Example. 12, 10, let's see. We should go on a break, right? So, why don't go in a break before we 40, yeah, let's take a break for now. Break 12:10 p.m. to 12:25 p.m. before we all get burned out, right? So I'll see you in 15 minutes. Stop sharing. I'm back here. Okay, so let's take a look at this specific problem example in the book that applies to rigid bodies, to a rigid body. In this case, it's a rigid body. It's not bending. It's not flexing. It's a rigid board, okay? 3.9 meters long and negligible mass. You can neglect its mass. A diver has a weight of 530 newtons. He's on the extreme right of the board. And there is a bolt on the extreme left of the board. There is also a fulcrum, 1.4 meters. So the situation is the following. The board is in net equilibrium. Find the forces at the board and the fulcrum. This type of problem is important for civil engineers, people that are building bridges and buildings. It's the simplest of problems that you're going to see out there, but it's very important. Okay, so here you go. Here's the situation. Here's the board. Okay, there's a fulcrum. Let's see here. The board is rigid. Okay, it's not bending. Remember that. We are all used to a board that's going to bend right when the diver step on it, right? And let's see. Bolt on the stream left. Okay. Here's a bolt. Here's the bolt here. Okay, and here's the fulcrum. Diver. So what we have to do, you have to apply the forces to this problem. Let's see if I have here my, oh yeah, I do have it here. Here you go. Here's the situation, board. Let's play the movie, just like I do. Here you go. Start with the fulcrum, right? Start with the fulcrum. Fulcrum. We apply the board to the top of the fulcrum. Then we bolt the board to the floor. Bolt the board to the floor. And what else? We're going to put a diver on the other end of the board. Right? Let's play it again. Here you go. Fulcrum, board, bolt, and diver. We want to know the force that the bolt applies to the board and the force that the fulcrum applies to the board. And we can do that. And don't forget, this whole thing is in equilibrium, static equilibrium. This whole set is the static equilibrium. Because it is in static equilibrium, the net force and the net torque must be zero. Must be zero. Okay, so let's identify the forces now. The diver has a weight, and that weight is transferred to this end, to the extreme of the board. Okay. is the normal force that the diver is applying to the board. That's what it is, right? Which ends up being equal to the weight of the diver. Okay, we know that the board is in equilibrium, static equilibrium. So in order to cancel this force here, we must have another force that's going to counter the weight. And then, we're going to have the force of the boat too. That's going to be either downwards or upwards. Okay, let's see. It has to be downwards, right? It has to be downwards because if it were, let's see, if it were upwards, yeah, if it has to be downwards. Why it has to be downwards? Because this weight is applying a clockwise torque on this board. In order to cancel this clockwise torque, the force that the boat is exerting on the torque that the boat is exerting on the board must counter the torque of the weight. Just by analyzing the situation, we know that this force here has to be downwards. Okay? And we are talking about the point of rotation is this one right in here. Okay, so let's write it down. Here you go. Let's write it down what I just told you. This is just a qualitative examination of the problem, right? Yeah, here you go. Move upwards, move upwards, okay? The weight, there are three forces. There are three forces. One, the weight of the diver on the extreme right of the board. Two, the force, the fulcrum is applying to the board the downwards, right? Downwards weight. The diver is applying to the extreme right of the board. The force the fulcrum is applying to the board. This force must be upwards to cancel the weight of the diver. Three, the force the boat is applying to the board, okay? This force must be downwards to counter the torque of the weight of the diver. Okay, that's just a qualitative solution of the problem. We didn't finish it solving it yet. Now we have to come up with a mathematical solution of the problem. Okay, because the board is in static equilibrium, the net force and net torque must be equal to 0. Okay? That's the condition for equilibrium, which parallels the Newton's first law. Note that this condition parallel. Note that this condition parallels Newton's first law. Okay, and now we are going to write down the mathematical equations. We go right in here. The condition for equilibrium. Like that, right? So should be a one-dimensional problem, so we can remove the vector symbol, right? Net force. Net force is equal to the weight of the diver, which is downwards. That's why I'm putting a negative sign in there. The force that the fulcrum is applying, which is upwards, and the force that the bolt is applying, which, by the way, is negative. I'm going to put F sub B, okay? The net torque must be equal, and by the way, it's also one dimension. This problem is also a one-dimensional problem in the torque, right? So I can use a scalar equation instead. It has to be the torque of the weight. The torque of the weight is clockwise. So let's put a negative sign here. The torque is going to be the torque of the fulcrum. And we also have the torque of the bolt. Like that. The torque of the bolt is going to be positive because it has to cancel. This torque here is going to be 0. Okay, because why is that? Because the point of rotation is the fulcrum. Since the point of rotation of the board is on the fulcrum, its torque must be 0. 12:37, we are almost there, right? 13 more minutes to go. Let's see if we can finish that. Okay, so here you go. I'm going to put it equal to 0. We have W. W was given. What is not known is this guy here. This guy and this guy. Right? This one also is going to be 0. And the torque of the diver is going to be the weight of the diver times the distance that the diver is from the fulcrum. The torque of the fulcrum is 0 because the board is rotating around the fulcrum. Consequently, the vector position of the point of application of this force, of the fulcrum force, is 0. And here you go. We have this here, the force that the bolt is applying to the board times that the distance that the bolt is from the point of rotation. Going back here, we go. That was the next slide. Tell you, here you go, R1. I put it R1. Let me just write it both, right? Let's use here is not true, right? Here is fulcrum. What is unknown is this guy. Everything else we know. Two unknowns, two equations. Okay, so we have RW, we have RB. Let's take a look here. RB, the board is 3.9 meters. Board is on the extreme left. Fulcrum, 1.4 meters. Okay. I just want, let's see here. RW is 2.5 meters. R1, 1.4 meters. So here you go. 2.5, 1.4. Let's see, it's 3.9 total, right? Yeah, 3.9. Okay. So 2.5, 1.4. So I'm just gonna leave it in symbolic format, and then you can put the numbers there, right? Here you go. What I'm gonna do? What I can do is eliminate one of the unknowns. The unknown that I'm going to eliminate is this one here. And by eliminating, what do I mean by eliminating? I mean, I have to write this unknown in terms of the other parameters that are known. Here you go. This is going to go to the right side. Change the sign. And the R position of the bolt goes to the right side as well. So we know what's the value of the force that the bolt is applying to the board. And to find out the force that the fulcrum is applying to the board, we substitute right in here and solve for the unknown parameter, the force that the fulcrum is applying. We pass to the right. We pass this one to the right. Here you go. We solve the problem, right? Just substitute the values. Okay, let's see if I got the numerical value here. No, I didn't. I didn't get the numerical value. But it's just a matter of plugging the numbers. RW over R1F. Yeah, let's see. Put it in a nicer format. Right here. Here you go. One here. Yep. Did you get the idea for those problems? Let's see if we have another example. We don't have another, but they follow the same logic. Okay, what I wanna, let me draw another table similar to that other one that I drew. Yeah, this one here, right? Uniform motion. Let's see here. Yeah, I need a table just like that. Well, what we need to do now, is to put another row here. Okay, Newton's first law applied to the linear case and the angular case, right? That's what we need. So we have 5 more minutes to go. Let's see if I can draw this table and add the Newton's first law for the linear case and the Newton's first law for the angular case. Insert table 1, 2, 3. I think that's okay. 1, 2, position, displacement, velocity, right? Velocity. Let's put it this way. Okay. Position. Linear. Angular. X. Theta. Okay. Position. Next, velocity. V. Keep on 1, 2, 3. Here you go. And I'm gonna put omega here. Humble. Next is acceleration. A. Alpha. I'm putting those dots because I don't want the software to change the letter to a capitalized letter, the lowercase letter to a uppercase letter, okay? And then we have one more here, Newton's first law. Newton's first law. The linear case is F net equal to 0. The other case is F net equal to 0 and net torque equal to 0. Oops. Good. And then we're going to keep on adding more stuff here. We're gonna, since we have first law, we're gonna have a second law as well. Okay? F net is equal to MA. What time is that? 2 more minutes to go. Right? And here, net torque is going to be something else here. Something that replaces the mass, and this something is called the moment of inertia, and something else that replaces the linear acceleration. What replaces the linear acceleration is the angular acceleration. And by the way, the angular acceleration is also a vector, okay? We didn't cover that, but here you go, alpha. But we can, we don't need to use vectorial, okay? Let's make it simple for you all. Keep everything scalar. But don't forget, strictly speaking, those quantities, they are vectorial. Like that. Okay, this what you see right in here, I like to call it the angular mass, but it has a different name. It's called the moment of inertia. Okay, but this I has different equations for different objects. And I think we are done, right? Any questions about that? Let's move it 12:50. We're going to have a break, not a break. We're going to have office hours right now. If you want to talk to me, and I'll be here. Okay. So
Thank you.
see you on Wednesday.
Professor Eglon, can I ask you a question?
Sure, go ahead.
Thank you.
Oh, wait a minute.